Okay, let's talk about Kepler's laws. But before we do that, I want to clear up one thing on orbits to make sure that we're aware of this. If I say this, there's two cases that we can encounter. Very short distances and very long distances. So this is going to be like earthbound stuff, whirling around in circles. This is going to be like moons, planets, etc., stuff like that. Make sure that we understand this. Okay, so in this case, centripetal force is equal to weight, so therefore mv squared over r is equal to m times g. M's cancel out. V squared is equal to r times g, so v is equal to the square root of r times g. So in that case, that's what you're going to use if you have a short distance. If you're talking about something on the earth, somebody throwing a discus, anything that's whirling around in a circle, that's what you're going to use. For longer distances, actually the same equation works out. But here's a key thing with the longer distances. If I go to longer distances, remember that g changes. This works any place where g is going to stay the same. And g doesn't stay the same when you're talking about long distances. G changes. So let's take a look at that. Now, if I go back to this, F is equal to g m1 m2 over r squared. And again, I say that is equal to weight. mg is equal to g m1 m. But this is the mass of the planet divided the distance away from the planet. So now if I get rid of the m's, I get g is equal to g mass of the planet times the distance between them squared. If I put that in that top equation, I now get v is equal to the square root of, let me see, I'm going to have r and big G and the mass of the planet and r squared. One of your r's cancel out. But now what happens as r goes up, v goes down. So understand that's kind of important. So when this is again when we're dealing with planets. Well, Kepler's laws deals with planets. Kepler was a noted astronomer from the 1600s, if memory serves me correct. And he studied tons and tons of data. He gets the credit for it. A guy by the name of Tycho Brahe, or Tycho Brahe, depending on how you say it, meticulously mapped the planets and the stars for years. So Kepler compiled all his data, and he came up with 3 laws. Now, inherently, they're not really in AP Physics 1, but the concepts can cover and help us with other topics. First of all, he said the planet's orbits are elliptical. Now, they're somewhat close to being circles. They don't have a giant eccentricity, but they are actually elliptical. I don't think you're ever going to see that on a test. You will see this, though. Number 1, a line from the sun to a planet traces out equal area. That's easier to see from a picture. So let me do this. If I have this, that's my sun, that's my planet, they're elliptical. What's it's going to say is this. That area is going to be the same as that area. This is the same time. Now, there's 2 ways to think about that, and there's 2 things that come out of that help us. First of all, something we haven't talked about yet is angular momentum. More on that in the next unit. Angular momentum is L. It's equal to mv times r. Well, if you think about it, momentum is m times v. So angular, we're simply adding a radius to it. What that says, obviously, that's going to stay the same. So what that says is as v goes up, as r goes down. In other words, a planet that's closer to the sun is going to have to move faster. So what's going to happen is when the planet's over here, it's actually faster from a linear point of view. Now, I can also see that from conservation of regular energy. Conservation of mechanical energy is another way to think about it, because here I would have more PE Here I would have more KE. So I think that's another way also to think about it. But it basically says as you get closer, which backs up what our thinking was earlier, as you get closer to the sun, you actually move faster if you're closer. And you see that even within the orbit of one planet. Kepler's third law says that t squared, which is the time for one revolution, over r cubed, which is the average distance, is equal to a constant. Now, that per se might not be on there, but let's see where it comes from. Where it comes from is this. I'm going to say that Fg is equal to Fc, like we've done before, and I'm going to come up with Mg is equal to big G, M1, M2 over R squared, like we've done before. We cancel out M's like we did before. Oh, let's do that. Let's scratch that. Let's set that equal to mv squared over r. I need to go with what my initial equation was. So I have that. Now, when the m's cancel out, one of my r's cancels out, like that. So I get the gm2 over r is equal to v squared, same thing as we had before. But now what I'm going to do is I'm going to approximate it with a circle. And we know the speed around a circle is equal to 2 pi r over the time for one revolution. In other words, circumference over revolution. So now what we'll do is we'll put that in and square it for v squared. So now what I'm going to do is plug that in over here. And what I'm going to get when I do that is I'm going to get that g m over r is equal to, well, this is going to be 4 pi squared r squared over t squared. Okay, now let's cross multiply here, and I get t squared over here, goes to the top, and I get, so t squared times g times m is equal to pi times r cubed. So watch this. Presto changeo, a little magic here. I get that t squared over r cubed is equal to 4 pi squared, I lost the squared there somewhere, divided by gm. The key thing to understand is that's a constant. Kepler was right. 400 years ago, he was right. And again, I don't think you need to necessarily know this, but realize you can derive that based on what you saw. More on this in class.